Hi, everybody. Welcome to day 9. Today's going to be an extended case study, sort of putting your functional programming skills to the test. There's one hard function for us to write, and there's a bunch of interesting concepts that we want to introduce. Concepts that you'll see again in CS62 or maybe in 140. But in either case, I want to just give you a taste of sort of like how do you integrate all this stuff. So far, we've been writing exercises. What's a real program? Let's write a real function that does something really interesting. So the case study we're going to use is about DNA edit distance. So when biologists look at two pieces of DNA or RNA, they might ask, how similar are these two pieces of DNA? And they might care about that for a number of reasons. One, you might care about, say, doing some kind of analysis to see whether it's an expected strand of DNA. Another reason you might do it is, well, you have two species and you'd like to know how closely related they are. Notionally, if their DNA is more similar in sort of spots of variation, then they're probably more closely related. Um, Now, there's a bunch of like interesting things that like complicate that story, and biologists are really good at thinking about this. Turns out I'm not so good at thinking about this, and that's fine because really we're just going to define the similarity measure. Our general goal is given two strands of DNA, be able to just assign a number. How close together are they? The lower the number, the more similar they are. So this is a measure. It's called a measure of similarity. And for us, the measure of similarity will work that like if they're identical strands of DNA, we'll just say it's cool at a distance is 0. Um, if there's one small change, right, one C gets flipped to a G, we would call it an at a distance of 1, and so on. So that's what we're going to do. Uh, we're going to define this for DNA strands, though the general algorithm that we'll be studying is due to a guy named Vladimir Levenshtein who discovered it in the Soviet Union, and I think that's the 60s. Um, for them, it's just a general notion of strings, any kind of list of like fixed characters. You can talk about this edit. And this edit distance shows up in lots of places, not just bioinformatics. It's the core idea behind, say, spell check, right? The suggestion from a spell checker is for words that have low edit distance, words that are really similar to the thing that you typed, but the thing you typed isn't in the dictionary. So they find things in the dictionary that are really similar. Okay, that's the general background. For us to get started, let's look at some examples and then think about what exactly we mean by an edit. So I think it's really helpful to have running examples to like pick a couple of things and then sort of look at how they're related. And choosing good running examples matters a lot. So I've kind of rigged the game to choose running examples that will lead us toward the solution that we want. Of course, if you're figuring this out yourself, you don't get that benefit. Vladimir Levenstein had to do this the hard way. We don't. Okay, let's get started. So here's a source strand of DNA. Right, this is what I'm going to think of as where we're starting. Right, if we're doing an evolutionary tree, maybe this is the root of the tree we think, or some organism that's well studied, and then we have other organisms whose DNA we want to look at. That's okay. It's similar. We know they're similar things. Like this is one kind of vole, and we're looking at other voles, whatever it is. Um, and we just want to compare each of them. So each of these target DNA strands represents sort of a different strand of DNA that you can, if you look at it, you can see there's something in common. Say maybe we're studying cats. My understanding is that the DNA of cats doesn't spell the word cat like any more frequently than any other thing. But like maybe I'm wrong. I'd love to be wrong. Wouldn't that be interesting? So anyway, you can see that all of these have sort of a common element. And before I sort of reveal what our model of edits are, I want you to think for a minute like how would you describe the changes that go from DNA source to DNA target 1 or from DNA source to DNA target 2 or from DNA source to DNA target 3? Before you can come up with a technical, formal definition in code, you need to have sort of an informal, personal understanding of what you think these things mean. So think about it for a second. Pause the video if you need to. I'm going to have a sip of my coffee. I put in too much sweetened condensed milk, but I actually have never. Okay, so let me give you my story for these. Yours might be different. And a different story of these edits will lead to a different formal notion of edits, which will lead to a different algorithm. So we're going to use my notion because my notion is the one that is Vladimir Levenstein's notion, and like that's the one we're going to build. But it's important for you to sort of compare, contrast, and just see. Look, there's a bunch of choices here, right? You can come up with different notions of edit, and that's going to give you different algorithms. There's people who just study that kind of thing. So let's take a look. So here's how I would talk about these edits. So to change DNA source into DNA target 1, we should replace the first G, substituting it for with a T, for a T, with a T. To change DNA source into DNA target 2, we should just delete the first G. To change DNA source into DNA target 3, we should delete the first G and add a G at the end. Now, you could have come up with reasonably very different edits. So what kind of edits do I use here? Well, so we have a substitution here. We have a deletion here. Here we have a deletion and an addition. And then in all these examples, there's this sort of implicit, and then I leave alone the parts that are the same. This idea of like there's parts that we're just not going to change at all. Those are those are sort of the different notions we've had. You could talk about other things, like you could say, oh, to get from gcat to catg, swap the g along 3 times. It's a different notion of edit. It's just a different thing. The idea that like, oh, you can have this movement. Another way to get from gcat to catg is turn the g into a c, turn the c into an a, turn the a into a t, turn the t into a g. Now, to me, that's sort of like a less minimal edit in some sense than what I said, right? Where I just said, oh, just move the G to the end and leave the CAT alone. But like, okay, different ways of doing it, right? For any notion of edit, we'll probably have different ways of building the string. In general, we'll probably always have this opportunity to just, we'll delete the whole string and reconstruct the whole thing. And okay, that's true. It's a way to get from one thing to another. But when your DNA is, millions of bases long, that's probably not how we got there, right? They probably didn't start from scratch, right? There was some mutation, some changes, metathesis, all these things that happen in DNA. Okay, hopefully this model informally makes some sense. What are we going to talk about? We're going to talk about substitution. We're going to talk about deletion and addition, and then we're going to talk about copying. So let's make it formal. Let's look at a definition of edits. Here's an edit. Oh, that did. Here are the edits. So there's 4 notions of edit. There's the copy edit, which says, hey, whatever source strand, whatever base I have in my source strand, just copy that base over. Right? So each of these edits is implicitly saying what to do with one base of the source strand. The delete edit says, oh, get rid of this one. We don't need it. The add edit says, leave the source strand alone. I'd like to insert something new here. And the substitute edit says, replace whatever's in the source edit with this. Now, there's some text here that explains, look, you could do this a bunch of different ways. We're following the way that Levenshtein did it, okay, in 1966. Couldn't remember the year. The article on this is really helpful. They detail on that page the sort of matrix-based algorithm, which is the efficient way to implement Levenshtein's edit distance. Maybe once you've watched these videos, go and look at the Wikipedia page. You could look at it first if you kind of want to spoil the surprise. We're building it all a little differently, in part because of how Coq works, and in part because I'd like to sort of show you the underlying intuition of what Levenshtein is doing. Okay, that's enough for now. That's the general notion of edits. In the next video, I'll be talking about cost and how we sort of talk about an edit being minimal, which is a sense that I gave earlier. And then in the video after that, we'll start to look at how you can actually start running these edits on a strand of DNA to see where we get. Okay, should be fun. I hope you all enjoy this sort of concrete example. I get that biology is not everybody's bag. Choosing a case study, you got to choose something, and I wanted something that didn't involve numbers. So hopefully this is still cool for you. And I'll see you in the next video. Talk to you all soon.